great. And we are live. Oh, well, here we are again, and your friend of mine, the Pillsbury Doughboy, standing in for Carl. Well, I know it looks like it. So, anyway, couple things going on here. We've got boxes all around. We've got a new television switcher coming. That's not a small item. It's huge. It's a 4K switcher with 20 inputs. This is a full TV station television production switcher. 4K with all the bells and whistles and like 6 upstream chroma keys and downstream third screen titling and all kinds of neat things. Because some of our chroma key, as you take a look at our boxes sparkling tonight, they're not supposed to do that, but they are, but they won't after we get the new equipment installed. It's just that's part of our regular production is doing that. Okay, so got a lot of stuff over here that is actually part of the version 2 of our new COVID incinerator. And I'm going to slip around here just for a second, talk about this thing. If you can kind of imagine, if those of you who remember the first one, this is the second one. It's bigger, yeah, like you couldn't tell. So this thing has 10 UV bulbs 3 feet long, 150 watts of pure 253.7 nanometer UVC light. This thing will generate over 1,000 cubic feet per minute of COVID-free air, and it's going to be a really valuable tool because this is like for bus stations, train stations, airports, places where you have large volumes of air and you need to turn them over very rapidly. This will allow all of that air to get rotated several times an hour, and that's what it takes to knock the statistical probability of infection down. You've got to get the COVID out of the atmosphere. It is an aerosol, we know that now. It is also something that we can slow down with masks, but the real solution, if you want to stop it cold, short of a vaccine, is what we're wearing, which is this headgear. This headgear prevents it from entering above the neck, just cuts it right off, and that, of course, is a huge win, but it does slow you down to wear this stuff. We're getting better at it, though. We're learning what to do and what not to do. We're putting anti-fog on the inside, learning not to spit on our visors. That's not fun to look through. All kinds of things. Real life, the practicality of doing something like this is always different than the textbook. You think, gee, you buy A, B, C, and you put it together, should work fine. And then you get out in the usability study and you find out there's all kinds of surprises. Anyway, tonight we're going to do something a little different. We're going to visit chemistry, but we're going to do it in a significantly different way. We're going to visit the enchanting part of chemistry. Look at just how much fun you can have with it. I don't want to steal David's thunder. There's all kinds of things that are springing into my mind, but he's going to say them anyway. So I'll wait to find out whether he says them, and then if he doesn't say them, I'll write them up and stick them on the website. But anyway, David, why don't you go ahead and come on up? I'm going to give you a chance to amaze and titillate these young people with some things that only 25 years can teach. Thank you.
Thank you. 2 weeks ago, we were working with a spectrophotometer, and you were given a homework assignment to do a graph. I thought it was a pretty small assignment, pretty easy. But I was proved wrong. A large number of people didn't do it. Some turned it in late, and I hope you realize that when you get out in the real world, if you don't do things on time, your boss fires you without even giving it a second thought. But I went ahead and pulled out an example. I'm not going to say who did it. This is a beautiful chart somebody made giving the dilution and in milligrams per milliliter for the albumin, and the spectrophotometer absorbance. It doesn't have the units, but then I neglected to tell you what the units are. So that's okay. They're ODs, optical density. But that doesn't really matter. This is a graph. 2 people turned this one in. And I was just wondering if any of you could make a suggestion about what could be improved on that graph. Just anything.
Like labels
Of
I forget, it's like I guess the X and the Y.
Yeah, the axes. There's no labels here, so you don't know what they are. That's a very valid point. It's an excellent point. I would throw in this label, the title. It's a bit vague. It's not really saying what it was about. Now, if it said something like albumin concentration, that's a nice short title. It tells what it's about. Okay? Any other suggestions on this? And people at home, feel free to comment.
We can't quite see part of the graph. Could we zoom in or change the angle?
I don't know.
Hang on.
But that's a good suggestion. And they don't need to see this table now, Carl, so if we can focus just on the graph. Anything else?
I think that the y-axis scale could be a little different so that you could see the results more clearly.
Yeah, that's a really good thought there. As a matter of fact, if that were one of my students in my classroom, I'd be yelling at them right now. Because look at all this wasted space. And since it's all down here, it's kind of hard to tell what's going on. You're not getting much difference in the samples.
I think I would add a trend line maybe to see where the data is going, like a line of best fit.
Yeah, they can either connect the dots. Now that's the most dangerous thing you could do in my classroom. I yell at students for connecting the dots. I know in math that's what they make you do. But in science, we do not connect the dots. We do what we call the best fit line or a linear regression and find out what would best fit, in this case, a straight line you would like to have. And I'd suggest it might be hard to make a good straight line out of that. Any other comments about it? All right, let's go to the graphing PowerPoint. By the way, in my classroom, that would have gotten probably 10 points for effort out of 100. And that's why I'm going to talk to you tonight at first about graphing. How do you make a graph? How do you interpret the graph? How do you know what it's saying to you? Because graphing is extremely important. Now, I'll talk a little bit about if you're doing hand-drawn graphs, but anything you're going to do for publication, it needs to be on a computer like that. Thank you,
Okay,
sir.
could you back up a little bit?
So graphing, how to make and interpret a linear graph. And of course, not all graphing is linear, but that's what we're going to talk about tonight. So why make a graph? It's extra work. It's a pictorial representation of the data for a clearer understanding. A picture's worth 1,000 words. It's also easier to see trends in the data. You mentioned a trend line. Exactly. You want to see what the trends of your data are. Is there some conclusion you can draw from that? It's also easier to compare different sets of data. Now, in this case, we only had one set of data. But sometimes you have different sets and you want to compare them and say, are they similar? Are they giving the same results and predictions? A graph can also lead to testable predictions. You make a prediction based on what you see in the graph and then find out if it really does that. So we're going to look at the parts of a graph. And the first part is the title. A title should be an explanation of what you're graphing. Can we make the PowerPoint on top of the... Yeah, very good. It should be succinct and clear. I have seen titles for a graph that took 3 lines. That's not a good idea. Make it short. Make it about what that graph is about. An explanation. Very simple. Like on this graph, I think albumin concentrations would have been really great. The axes. Y'all mentioned that. Label the units. Well, first, label the axes. What are they? And what the units are. Now, this may be difficult, but can anybody guess what the x-axis label would be on that graph? Those of you who did the graph, you had these real nice straight lines. And that one is oddly shaped. I think they graphed the wrong thing. I think they graphed the tube numbers for the x-axis instead of the concentration in milligrams per milliliter of the albumin. And that would have made a big difference. They'd have had a very different graph. Choose an appropriate scale for your graph. this is a problem I've had with a lot of students. So this y-axis, as you mentioned, that needed to be spread out more to have the data taking up the whole graph. There's no sense in having those parts that aren't being used. And it makes it much more accurate to read the graph. Never change the scale in the middle of a graph. I've seen a student go, okay, this square, 1, next square 2, then 3, then 4, then 5, the next square 10, then 100, then 1,000. You can't do that. You have to use the same scale throughout, or it makes no sense. The x-axis should be your manipulated variable. Now, what do I mean by manipulated variable? Or more specifically, what was the manipulated variable in that lab?
The concentration.
Yes, absolutely. Not the tube number. Yes, you did change tubes, but what was important was the concentration in those tubes. And if that was graphed, you got a beautiful graph. And the y-axis would then be your responding variable. What was responding in this graph? In the graph?
The absorbance.
Yes, because as you change the concentration, it changes the absorbance. So that was the response to what you manipulated. The data points. If you're doing it by hand, data points should be very, very, very tiny points, barely visible. And then you, if it's a hand-drawn one with these very small points, you put a circle around each one so that you can find that point again later, because it gets very hard to locate them. Of course, with a computerized graph, that is much simpler. If there are multiple trials, now we did not do multiple trials, but if you did, then each dot should be put at the average of the multiple trials. All the same data, same circumstances, same variables, just a different try. So it was another trial. Each dot should be at the average, and then you draw a small vertical bar through the dot. And the top of the bar, and you put a horizontal, tiny horizontal line at the top of the bar, would be the maximum in that data range. And the bottom of the bar would be the minimum. So that way you can see just how well the data was acting. If you end up with a line that takes up the entire vertical scale of the graph, that means something's wrong. Your results were not repeatable. The best fit line. This is one that my students had struggled with a lot. And I understand that. It's not easy. Never connect the dots. Only in a math class, not in a science class. It's best to use a program. A computer program can give you a best fit line. It'll use something like linear regression or exponential smoothing, some method of getting an equation that fits that line. What is the equation that fits a line? What do we call that? Many of you actually put it on your graph.
Line of best fit.
I couldn't hear that.
Line of best fit.
Line of best fit.
Well, that's the line. But what's the equation that describes that line? In its simplest terms, it's y equals mx plus b. Now, in that, y, of course, is the values on the y-axis. X, the values on the x-axis. What's m?
The slope.
The slope, that's exactly right. Why did we use m for the slope? I have no idea. I'll blame that on the mathematicians, although we scientists do enough crazy stuff. So yeah, y equals mx plus b is the equation for a line. What is the b?
The y-intercept.
Excellent. The y-intercept. So that if x is 0, then mx is 0, y equals b, the y-intercept. And that's how you can then use that equation and figure out your unknown. So if you're doing a hand-drawn graph, which I don't recommend, but sometimes it's necessary. Like you need to put a graph in your logbook of your research so that you can figure out what's going on. If it's done by hand, you have to eyeball that hand-drawn line. You try to do it so that some of the points are on the line, and the ones that are above the line are about just as far above as the ones that are below the line are below that. I never took off points for a student doing a poor job on a best fit line because it is a judgment call. I would then show them a better fit line, a better best fit line, but I wouldn't, make that cost them. A key, if you're going to have more than one line on a graph, then you have to have a way of identifying which line is which. And so you use different colors or different symbols to tell them apart. Some people will put squares for their dots of one line, circles for their dots of another one, so on. Some people use a dotted line or a dot dash line, different ways that you can differentiate them. But then you have to put a key on there that tells you what those colors or symbols mean.
Someone, I heard someone has a question.
I think that was me chastising myself for hitting the wrong button.
Oh, got it.
You then need a key to identify what the colors or symbols mean, as we said. The unknown. That's what it's all about. Can you determine what the unknown is? You should indicate on the graph where the unknown is located. Put a dot or something and make sure you label that that's the unknown so that people know. It should not be part of your calculation for the slope of the line. It is permissible to use dotted lines to show where the unknown meets the axes. You could draw a dotted line horizontally to show where it hits the y-axis, one vertically to show where it hits the x-axis. Not required, but some people do that. If you're using the equation for a line, y equals mx plus b, you are solving for x. I have seen people flip them around. And because it says y equals, they put the y value in for the x and solve, and they get an answer that makes no sense. So that's how to do a linear graph properly. The elements that it should have. And again, what I would take off for not having them. Okay, next we're going to look at chemistry itself. So if we can get the PowerPoint up for chemistry. Technically, one could say I'm not a chemist. I got a Bachelor of Arts in Scientific Writing from Ohio State University. Then I went back and got a Bachelor of Science in Zoology from Ohio State University. Then I went into the Air Force and did biomedical research. And after a couple of years, I came out and went to University of Texas at San Antonio and did graduate studies in immunology, well, actually biology with a concentration in immunology. And I did a total of 10 years of biochemical research in biomedicine. Following that, I started teaching high school, and for most of my 25 years, I taught chemistry. And today I'm going to introduce you to some people that I like in chemistry. And one of them is the author of this book, A Grain of Salt, Dr. Joe Schwartz. And it's subtitled The Science and the Pseudoscience of What We Eat. I have a collection of all of his books, about 2 feet wide on my shelf. And he is my favorite author in chemistry. And what I really love about him is that he doesn't just tell you about chemical reactions, he uses them to explain about things that are going on in your life. And that's so much more important to me. And one of the people I follow on YouTube, he does very clever demonstrations of very complicated chemistry, but he never says anything about what it means, what it's used for. And I feel like he's really missing out on an opportunity there. Are any of you familiar with Hank Green? Okay,
I am.
thank you. Well, Hank Green is a YouTube personality. He's got a degree in chemistry, and he's done a variety of YouTube things. Voyages of Microcosmos, where he looks at microorganisms, one of my favorites. He did a lot of crash courses, and he has a unusual one that is he and his brother communicating with each other over the internet. And they do that twice a week.
Okay, David.
All right.
If I may just interrupt for a moment.
Yes, sir.
Couple, 3 things I want to cover. We had a situation develop last weekend that precipitated a significant change in our air system. And we are now drawing our air in from a colder source. That's the intent. I'd like you to join me tonight in monitoring the air and the air temperature. If at any point in time you sense something amiss, don't hesitate to speak up. Because anytime you make a change like that in the air system, we put a great big hole in the wall, we put a giant blower in, we made some significant changes. So if you sense anything that is uncomfortable or awkward or smells funny or whatever, I want to know about it right away, temperature-wise or in any other way. That's one. Number 2, you notice that Dave is not wearing the beanie tonight. That's not because he's afraid to put one on, because we messed up the air system. He actually is going to go outside and play with fire. And if you go outside and play with fire, that's not a good thing to do with a pressurized air system on your head. There's some safety things about that don't work out. So because he's going to go ahead and be a pyromaniac tonight, we thought best that he go ahead and operate without the beanie. The plus is we're safe from him. He may not be safe from us, but we're safe from him.
I'm expendable.
And no, and as long as one of us, if the rest of us are all suited up, one of us can unsuit. That's totally logical. And so probably going forward, especially if we have guest speakers, we're not going to put them through the rigor. In fact, we might even say, gee, why should they wear a face mask? But if we did that, then we can't use the UV lights. So there are some trade-offs. We're working through. trying to figure out what the best protocol is, but we definitely want to be able to get some people in here that can add to the flavor of what we're doing. Those things covered, we're going to go back to David. So David, you're live.
All right. And I'll be checking tomorrow to find out how much of a sunburn I get on my ears and my head from a fluorescent light. So, this is an introduction to chemistry. And I want to begin by showing you two very short videos about chemistry.
Over the last 52 weeks, I've enjoyed sharing with you my fascination with biology. If you've been through it with us, you've now got yourself a pretty deep and complex understanding of how cells work to the ecosystems that make the planet work. And it's never too late to catch up on those biology and ecology courses. They'll be here on YouTube forever. But it's time to move on to something bigger because it's smaller, more beautiful because it's invisible, more powerful because it's everything. Crash Course Chemistry. My undergraduate degree is actually in chemistry, and I've been a lifelong lover of this subject, not just the rules and the laws and the bonds and the coefficients, but of the men and women who shaped this science that deepened our understanding of the world so much. The Siberian misanthrope who would revolutionize our understanding of matter, the German war criminal who saved 1 billion lives, the French aristocrat who created the science of chemistry, and all he got for his trouble was beheaded. And of course, all of these stories exist within the greatest science ever. What is matter made of? How and when do atoms come together and break apart? What is an electron? Why is silver's chemical symbol Ag? How do we fix global warming and live forever? The answers to all of these questions, except for the last two, will be contained within this course. But those last two, if and when they get solved, I guarantee you, will be solved with the help of chemistry. And we'll be doing it in this beautiful new set that was designed and created by Nick Jenkins and our graphics team. Our graphics team will be Thought Cafe, which is what Thought Bubble has turned into. We're slaving away on Crash Course Chemistry now, and the first episode should be hitting your subscription box within the next couple of weeks. Until then, feel free to check out any of the biology that you may have missed, and we'll see you soon.
Try it again, Dave. You went the wrong way. You hit the wrong button.
Promise I didn't.
You're going up, not down.
I'm hitting the down.
Yeah, but you got the thing upside down.
Thank you. Boy, my face red.
Hello, I'm Hank Green and I want to teach you chemistry. But please, do not run away screaming. If you give me 5 minutes to try to convince you that chemistry is not torture, but instead the amazing and beautiful science of stuff, and if you give it a chance, it will not only blow your mind, but also give you a deeper understanding of your world. This is just my opinion here, but I think that understanding the world leads to a greater ability to enjoy the world, and there's nothing that helps you understand the world better than chemistry. Chemistry holds the secrets to how life first formed, how cancers are cured, how iPhones have bigger hard drives than 5-year-old laptops, and how life on this planet might just be able to continue thriving, even ours, if we play our cards right. Chemistry is the science of how 3 tiny particles, the proton, the neutron, and the electron, came together in trillions of combinations to form, get this, everything. Now, chemistry is a peculiar science, sometimes talked about as a bridge between the ultra-abstract world of particle physics and the more visible sciences like biology. But calling chemistry a bridge is like calling Eurasia an island. Chemistry has it all. Mad scientists, world-changing revelations, the practical, the impractical, medicine, bombs, food, beauty, destruction, life, and death. Answers to questions you never knew you had. I love chemistry, and I hope I can give you a glimpse into why. So today, Let's start out with maybe the biggest idea of all time and move on from there. Stuff is made from atoms.
So, chemistry is the study of matter. Is it really important? Well, it'd be nice to know about matter. It's called the central science because it connects the other areas of science. Everything is made of matter. So chemistry is the study of everything. That's why my Pinterest page says chemistry, because everything is chemistry. That's my title of it. Chemistry connects the physical sciences, the life sciences, and the applied sciences, such as medicine and engineering. So what is chemistry? Encyclopedia Britannica defines chemistry as the science that deals with the properties, composition, and structure of substances, defined as elements and compounds, the transformations they undergo, and the energy that is released or absorbed during the processes. So when did chemistry start? Basically, early man discovered fire and how to spread it. Very important discovery that made the big change for the people living then. They also learned how to make beer, which was much better for them, safer, for drinking than water was. Water was often contaminated. Beer, the alcohol, killed the organisms that were growing in it, which is why there was a show called Beer is Everything, where they traced the history of beer. He figured out how to improve spears by making them have fire-hardened tips, so they penetrated better, whether for protection or for fighting food. The first recorded chemist was a lady named Taputi. She was running wasn't a castle, but whatever it was that the head people lived in, she was in charge. And she made perfumes using chemistry in about 1200 BC. It was recorded on cuneiform tablets, the earliest known recording of a chemist, occurred in Mesopotamia and Babylonian rule. Later on, we had alchemists. They were the forerunners of chemists, and their main goal was to transmute lead into gold to make it more valuable. And of course, they never succeeded at that. They tried a lot of different things, and they killed themselves frequently. Now we can do it. We can turn lead into gold using a nuclear reactor, an extreme amount of money and energy, and for a very tiny product. Not a very logical thing. So who do we call the father of chemistry? There's a picture of him, and most people think it was Antoine Lavoisier, a nobleman who lived in France in the 18th century. He was doing something new. He was experimenting. Thanks to a man named Aristotle, who lived about, 2,000 years before that. For almost 2,000 years, nobody did experiments. If you wanted to know something, you looked it up to see what Aristotle said about it. Because as far as everyone was concerned, Aristotle was like a god. And they just all believed automatically what he said. But Lavoisier started doing experiments, and he came up with the law of conservation of mass, which is very central to our understanding of chemistry, that mass cannot be changed, cannot be created, cannot be destroyed. Now, we modified that because we added the law of conservation of energy, and we said that matter and energy, mass and energy, cannot be created or destroyed, only interconverted. When did that happen? When was it decided you could turn mass into energy?
Can you tell me who came up with that idea?
We are deficient in our knowledge of history. Anybody know what happened in 1945? What was going on in the world?
A man named Robert Oppenheimer had something to do with this.
The atomic bombs were dropped.
Say again, please.
The atomic bombs were dropped.
Yes! 2 of them exactly. Yeah. That was the first time we turned mass into energy.
Well, there was ones previous to that at Los Alamos
Yeah.
when we tested it to make sure, and that was where Oppenheimer was.
Yeah. And Lavoisier also isolated this gas called oxygen, which he found was involved in combustion and breathing. Prior to that, people said that things burned because they had phlogiston in them, and when they burned, it was releasing the phlogiston. And he came up with an experiment that proved that wasn't true. He also discovered hydrogen, another element. Unfortunately, he died when his head was removed by la guillotine. The French said la guillotine, she gives the closest shaves. But that was the penalty for being a nobleman in France at that time. What are physical and chemical properties? There's a lot of glare on there. Physical properties include things such as size, color, density, texture, odor, malleability. Anyone know what malleability is?
Is it the ability of a metal to flatten?
Yeah, change shape. It's malleable. So it can have its shape changed. That's what malleability. Ductility, another hard word. Anyone know what that means?
Able to stretch out into a wire?
Perfect. Exactly what it is. Changes in state, melting, boiling points, those are all physical properties of matter. So a physical change is when these properties, such as a change in state, are changed. But it does not produce a new substance. If you take ice, solid water, and melt it, you get liquid water. And if you boil it, you can get gaseous water, steam. And you can reverse those and turn that gaseous water back into ice. Chemical properties are, on the other hand, are the ability of a substance to react with another substance to produce something with new chemical properties. Chemical change gives a new substance. For example, if you take 2 molecules of hydrogen and 1 molecule of oxygen, combine them with a little bit of energy to get it started, and it forms 2 molecules of water. That's a chemical change. Properties of hydrogen and oxygen are not seen in the water molecule. It has very, very different properties. What is matter made of? Matter is anything that has mass and takes up space. And that's pretty much everything. I mean, you can talk about some emotions, maybe, love, faith. There's 118 known elements. You'll find them on the periodic table. 83 of those are naturally occurring. The rest of them are man-made. We made them. And when we look at the periodic table later on, we're going to find out how important it is that we've discovered element number 118 and what happens maybe if we find element 119. There's a lot of hope for that. The atom is the smallest part of an element that has all the properties of that element. If you take a smaller part, it will not have all the properties of the element. The atom is made up of 3 subatomic particles: protons, neutrons, and electrons. And there you have a diagram that shows, let's see what it says, carbon atom with its protons and neutrons in the nucleus and the electrons in orbit outside. That's what's called a Bohr model of the atom, because Bohr is the guy who came up with it, sometimes called the planetary model. Well, what is the atom? The positively charged protons determine the element's identity. If you say hydrogen has 1 proton, if you have an atom with 2 protons, it's not hydrogen anymore. Then it's helium. The number of those positively charged protons determines the element's identity and its atomic number. Gold, Au. Au is for aurum, Greek word for gold. And it has 79 protons. And any gold atom will have 79 protons, always. Different numbers of neutral neutrons give different isotopes of an element. For example, hydrogen has 1 proton. It has 0 neutrons. But what's called heavy hydrogen, also known as deuterium, has 1 proton and 1 neutron. And in the diagram there, it also shows tritium, which has 2 neutrons with the 1 proton. Those are all what are called isotopes of hydrogen. The number of protons and neutrons give the mass of the atom, and they are located in the nucleus. Now, putting together 2 of those statements, can you tell me what's the charge on the nucleus?
Positive.
Excellent. It's got protons and neutrons. Neutrons have no charge. Protons do. Protons are positive, so it makes for a positively charged nucleus. The negatively charged electrons orbit the nucleus, and their mass is negligible. Well, actually, we usually say it's electron's about 1/2000th the mass of a proton. Actually, I think it's 1 over 1,536 or something like that. Interestingly, a neutron is tiny, tiny bit heavier than a proton. About 1 over 1,536. Makes you wonder what a neutron really is. How do we represent the atom with models? There have been a number of theories. Excuse me. Dalton came up with the idea of the atom, and he thought it was just a cloud. And then we have the plum pudding model that J.P. Thomson came up with, in which he said that there's a positively charged atom with these negatively charged plums in it, like a pudding. And then you have Ernest Rutherford, who came up with the nuclear model. Interestingly enough, Marsden was Rutherford's assistant. Went to Rutherford and said, I've got this grad student, I need the project to keep him busy. And Rutherford said, well, have him beam some neutrons at gold, a sheet of gold, and he'll be able to detect all the neutrons bouncing back because the gold's a solid atom. But when the student did that, he found some of the atoms bounced back, most of them didn't. I mean, the neutrons. And Martian said, "You did it wrong. Do it again." Tried it several times, and it still happened. And then Rutherford put it together and published it because he was the scientist in charge, so he gets the credit. That we have a positively charged small nucleus in the center of the atom. And then Niels Bohr came up with the Bohr model, or also called the planetary model, which puts the electrons in different orbits. And that's important because all chemical reactions are based on electrons. That's all that matters, is electrons. And actually, it's only valence electrons. They're the ones that count, the ones in the outermost ring. And then the man came along, Schrödinger. Now, you may have heard about him and his cat. He had an experiment said if you put a cat in a box and you have a vial of poison in there and you have a radioactive nuclide that may or may not give off a radioactive particle at any given moment. And if it does, it causes the cyanide to be released and kills the cat. And if it doesn't, the cat's alive. So the question is, if the box is sealed and you can't see, is the cat alive or dead? And Schrödinger said, yes, it is alive or dead. He said, actually, it's both. Well, he also did another thing where he said that the electrons are in clouds. And this is the quantum model based on quantum theory. What he did was took an atom, theoretically, and said, okay, you graduate students, I want each one of you to calculate what are the odds of an electron being at that point. At that point, at that point, at that. And they did that. And they had no calculators, no computers. They did it with slide rules. Very laborious, time-consuming. And they calculated the probabilities, and we get something called the electron cloud model. And these are the electron orbitals. On the far left, those are the s orbitals. And this is arranged just like the periodic table. And then the far right are the p orbitals. Now, I like S's for sphere in my mind, and P is for peanut, because they're shaped like a peanut. And then in the middle, those elements are the d orbitals. I have no idea why. And they're really complicated. But even worse, the ones at the bottom are the f orbitals, and they are, I can't imagine them. I once asked a friend of mine who's supposed to be good at drawing to draw all those orbitals put together on one atom. And she gave up. She was really good, but she gave up on that one. It's complicated. Next question, what is the Lewis dot structure? I know that for some of you, this is a lot of just covering stuff you know. But it's still a good review for you. So if we look at the periodic table, just the elements 1 through 20, these are the Lewis dot diagrams. And what it is you have a dot for each electron in an element. And the dots, as you increase an atomic number across the row, you get more dots, more electrons. And we always put the electrons as if this were a square, and we put them on different sides until we hit 5. And when we hit 5, they pair up. So nitrogen has 1 on each side, but one side has 2 of them. And then helium, neon, argon, well, neon and argon have 8, helium has 2. And they are what are called noble gases. And they are noble, and like nobility, they don't mix with anybody, and they are unreactive, except for some really rare cases. What do the electrons actually do? All chemical reactions, all of them, involve only the electrons. The nucleus is only involved in nuclear reactions, not chemical reactions. Atoms combine with each other by losing, gaining, or sharing electrons. Those are their three options. The outermost, or valence electrons, are involved in these reactions. They're what makes it happen. They are. Almost all atoms want to have 8 valence electrons, and that is called the octet rule, an octet being 8. Now, there are some exceptions. Hydrogen, helium, lithium, beryllium, boron. It's easier for them to have just 2 electrons, to lose electrons to get down to being like the perfect gas, helium. Everybody wants to be like the noble gases. The reason is it's the lowest energy configuration for the atom. That's why they do it. It's not like they have a brain and think about this. It just happens. For the main group atoms, those are the s orbitals and the p orbitals, the column number is the number of valence electrons. I should have put in there that for the higher numbers, you get rid of the teens. So nitrogen is in column 15. Get rid of the teen, it's 5. Nitrogen has 5 valence electrons. Now this also shows which ones are metals, metalloids, and nonmetals. We can talk about that another time. How do those atoms then combine? An atom that loses an electron is a positively charged atom, which we call an ion, a positive ion. An atom that gains an electron is a negative ion. Oppositely charged ions are attracted to each other. Opposites attract, like boys attract girls sometimes. And they form strong ionic bonds. If an atom shares electrons, instead of stealing an electron, losing or gaining an electron, if it's actually shared, these atoms are nice to each other. They share their electrons. A weaker covalent bond is formed to make a molecule. So, using Lewis dot structures, we see for an ionic one, you have sodium and chlorine. Sodium will lose an electron so that it has a positive charge. Chlorine gains an electron so it has a negative charge. And so you have an ionic bond between the sodium ion and the chlorine ion. For covalent bonding, here we have 2 hydrogens. They will share those 2 electrons. And that way, each hydrogen has 2 electrons, although one of them is shared with its neighbor. Metallic bonding is a bit weirder. It's what we call a sea of electrons. And it means that electrons are just everywhere. They run throughout the whole metallic compound. Now, when ions form a compound, we call it an ionic compound. When we get a covalently bonded compound, we call that a molecule. How do we know which type of bond you're going to get? Is it going to be ionic or covalent? In general, a metal plus a nonmetal gives an ionic bond to form an ionic compound. Now, there's a more complicated way you can figure it out, but there's only rare exceptions to that. It's easier just to remember. A metal and a nonmetal is ionic. In general, a nonmetal and a nonmetal gives a covalent bond to form a molecule. In general, a metal plus another metal gives an alloy, like bronze. That's an alloy. How do we show covalent bonds with Lewis dot structures? Well, we can go through this process and The first one is carbon dioxide. And you find that in order for there to be a sharing, they're both nonmetals, to be shared, you're going to have 4 electrons between the oxygen and the carbon. 2 electrons make a bond. 4 electrons make a double bond. So that's an even stronger bond. And in the second one, a molecule of nitrogen, N2, we get 6 electrons between them being shared. That's called a triple bond. And that is a very, very strong bond. Very hard to break apart nitrogen. That's why it's basically an inert gas, and we breathe it in and it causes no problems for us. Fortunately, there are some organisms who can break down the nitrogen molecule. And for instance, bacteria in the roots of legumes, like peanuts, will do that. And then in the next one, it's using 3 elements with carbon, hydrogen, and bromine. And I'm not going to go into naming of compounds. That gets very, very complicated. How do I show the ionic bonds with Lewis dot structures? Because there, you don't draw a line for the bond. So with a positive sodium and a negative chlorine, on the negative atom, we show the 8 electrons around it, and then we put a plus or a minus sign on each one of them. And if you have magnesium and bromine, the charges on those are such that it takes 2 bromines to be attracted to 1 magnesium. And we'll see that better when we look at the periodic table later on. And it gets real complicated with aluminum and oxygen. Have any of you had chemistry and learned to cross-multiply to get your formulas?
Yeah, I have.
Okay, 1 person. Okay, that's good to know. It's a really nice technique that really simplifies the problem. How do we draw the Lewis dot structure for carbon dioxide? That's a complicated one. So we end up with getting 2 different structures. One of them has the carbon double bonded to each of the oxygens. However, that can flip around and have the carbon triple bonded to 1 oxygen and single bonded to the other oxygen. And flipping back and forth gives what's called resonance. And that ends up a much more stable, stronger bond. And that's why it's hard to break carbon dioxide apart. Unless you're dumb enough, I shouldn't say dumb enough, ignorant enough that you don't know that if you have a metal fire, you cannot put it out with a carbon dioxide fire extinguisher. Because a metal fire is so hot, it will break apart the carbon and oxygen and feed the fire with the oxygen and make it much worse. Some people found that out the hard way. So, I'm giving you a homework assignment. Again. And I'm going to give you 2 tables, and you're to complete those tables and email them back to me. And tomorrow, I will send out an email to everybody with those 2 tables on it. Okay? And all you got to do is fill it in. And use the periodic table to do that. It's the easiest way. Using the concept that we've covered this evening. Next thing I want to do is show you one of my favorite people, Andrew Seslow.
The science of chemistry has disappointed many people. it disappointed the Emperor of China in the year 59 BC. He had been told that one of his court officials, Liu Xiang, could make gold. A great feast was organized, at the end of which Liu Xiang was to prepare a small quantity of the precious metal. After toiling away with complicated apparatus for several hours, all he succeeded in producing was an unpleasant smell. Liu Xiang was executed on the spot. This true story reflects one of the problems which has confronted mankind since the dawn of civilization. The problem being understanding how substances change into different substances. This phenomenon of substances changing into different substances has now evolved into the grand science of chemistry. So what is chemistry? Chemistry is the science of substances and how they turn into different substances. And very frequently, we can recognize a chemical change because there is a change of color. As I pour my chemical water from one flask into another, you'll notice a color change. And this is because I am making a new substance on every occasion. Chemistry plays an important, a hugely important role in our everyday lives. Masses of substances and materials that we use on an everyday basis owe their existence thanks to the science of chemistry. Plastics, polymers, dyestuffs, detergents, perfumes, toothpaste, pharmaceuticals, fuels, explosives, a whole range of remarkable substances. Tap water, fizzy drinking water, masses of substances, fertilizers, owe their existence thanks to the science of chemistry. Chemistry, the science of substances and how they turn into different substances. Now here I've showed you some experiments with chemical waters, and I've illustrated for you the principle of what chemistry is about, substances changing into different substances. I'm now going to move to a different type of water, which I have in my container here. This type of water, which is by magicians called magic disappearing water. I will pour some into my beaker here, and I will now throw it into the air and show how it disappears. And I will stand under it there, and don't look for it, you won't find it. And the reason is it has disappeared into thin air. Why has it disappeared into thin air? Because that is what it is made of. This liquid which I have here represents one of the greatest triumphs of the science of physics. Physics is the science of matter and energy, and one of the greatest challenges of the science of physics in the 19th century was to be able to achieve temperatures which are low enough to turn the gases of air into liquids. And what I've got here is liquid nitrogen, and the liquid nitrogen has a boiling point of minus 196 degrees centigrade. Now, as you see, it's boiling away in my plastic bottle here, and the reason why it's boiling away is because this room is remarkably hot compared to the temperature of the liquid nitrogen. We here are at about 21, 22 degrees centigrade. Liquid nitrogen has a boiling point of minus 196, which is almost as cold as you can get anywhere in the universe. Absolute zero, the coldest temperature in the universe, attainable theoretically, is minus 273 degrees centigrade. Now, one of the golden rules when you have liquids which are boiling is never ever put them into containers which are tightly sealed. Well, that's precisely what I'm going to do now. I'm now going to have these Sprite bottles here, and I'm going to tightly put the stoppers on, and I'm going to gradually put them into these dustbins here. Now, the reason why you should never ever do this is because when liquids boil, they undergo a huge coefficient of expansion by a factor of about 800. I have poured in approximately 100 centimeters cubed of liquid nitrogen into each of these bottles, and that 100 centimeters cubed will expand into about 80 liters. Now, these bottles have a volume of 0.5 of a liter, and therefore when that liquid nitrogen evaporates, it will occupy about 80 liters. It will generate a pressure of about 160 atmospheres. Now, these bottles, very clever though they are, made of brilliant polymers, they will just simply not withstand that pressure, and therefore they may explode. They don't always
I've
explode.
done all the
but when
demos
they
he
do
does in this
explode,
show,
the,
except this one.
noise is really
I've
quite
never had the nerve
substantial,
to
and
do
that's
it.
why, for safety reasons, I have put them into the bins. Now, that will continue to boil away. You may hear very loud bangs, so please be warned. But in the meantime, I'd like to show a couple of fairly obvious experiments with liquid nitrogen. The most obvious one being, of course, is to freeze some water. Water freezes at 0 degrees centigrade, and I will pour a small quantity of water into here and cover it with liquid nitrogen. So there goes our water there, and I shall now pour liquid nitrogen on it, and that will obviously turn the water into ice. Now, unlike the experiments which I did with my chemical waters, when I mixed chemical waters which were colorless together, and you saw a color change because a new substance was being made, here we have a totally different type of effect. You see, there is no color change at all. And that is because here we have a physical effect. The two colorless liquids, which I have mixed together, are now changing their state. They're changing, one of them is changing from the liquid state to the solid state, that is the water, and the other one, the nitrogen, liquid nitrogen, is turning from the liquid state to the gaseous state. So here we have the three states of matter in one very straightforward experiment. Now, as the liquid nitrogen continues to boil away, you may hear a slight crackling sound. Now, this is because when water freezes, it expands slightly, and as it expands, the crystals take up a greater area, and they push, a volume, should I say, and they push against one another, and sometimes this may lead, it sets up enormous mechanical forces, which is what the crackling is about, and sometimes the beaker may actually crack. So we shall keep our eyes on this, allow the process to continue, and I can just hear the beginnings of a crackling sound. Now, just top it up, make sure we continue to freeze our water. And I wanted to tell you that when liquid nitrogen was first made at the end of the 19th century, it did set off an entirely new era in the history of technology, and that's liquid gas technology. And thanks to that, today we have frozen food, we have a huge number of all sorts of effects that we benefit from. Among them, of course, are refrigerators. Now, to continue then on our experiments, and also the science of cryogenics. To continue with our experiments with low temperatures, these, by the way, approximately 5 to 6 minutes, you'll hear the bangs, so please be warned. I'm now going to show you an experiment with a solid. Here we have a piece of rubber tubing, and it's elastic. The reason why it's elastic is because when you stretch it, it returns back to its original shape. Now, the reason why it's elastic is because I can hear the pressure being taken up, so you may hear a bang shortly. Now, the reason why it's elastic from a thermodynamic point of view is because it's very warm in here. And because it's very warm in here, these molecules in here have lots of energy. However, I will now place the rubber tubing into liquid nitrogen, and please observe carefully what happens as we lower the temperature. And you'll notice this most interesting effect, you see, of a shower which is issuing from the end of the rubber tube. Now, why does this happen? Well, it's for the same reason that the bottles are exploding in there. And that is because as the liquid nitrogen boils fiercely when it comes into contact with the very hot rubber tubing, so it expands enormously, as I said, by a factor of about 800. That boiling, therefore, pushes the liquid nitrogen out, setting up a pressure that forces it out there. As you saw there, we didn't have anywhere to escape, and that's why the bottle finally gave way. Now let us inspect our rubber tubing which we have here, and let us see what has happened to the elastic property. It went in as an elastic solid, but now you see it's no longer elastic, and if I whack it one on this table, please watch carefully, then it will shatter into 1,000 fragments. Now, the reason why it shatters into 1,000 fragments is because at high temperatures, the molecules are all vibrating. We have lots of energy. The molecules of the rubber tubing have lots of energy, so they're all going around like that. But when you drop them into liquid nitrogen, there is very little energy, and so the molecules suddenly freeze. They go like this. They freeze solid. I'm, of course, being silly, but I'm illustrating an important scientific principle. Now, I wanted just to show you here, we're just going to see, in the meantime, I just wanted to show you our beaker has indeed cracked. There it is. There's a piece of glass has fallen away from it. And what that shows you is, it just shows you the huge forces, intermolecular forces, which are set up when water freezes. It freezes, the molecules rearrange themselves to form an open lattice. Now, here I have a beautiful balloon. A beautiful balloon, and why does it have the pressure? It has pressure inside it because the molecules of nitrogen and oxygen in the air are moving around because they have lots of energy, because it's very warm. But if we reduce the energy by pouring liquid nitrogen over the balloon, then you will notice a very, very interesting effect. So please watch carefully. I'm going to pour liquid nitrogen over the balloon, and as you notice, the balloon starts to contract. And as the balloon starts to contract, so you'll notice getting smaller and smaller, and it takes a very, very a shape which has there's no elasticity. It has completely collapsed. Now, why is this? Well, once again, it's the same reason. At the low temperatures, sorry, I think the floor's cracking underneath me. So everything's freezing all around, but we're still all right. Please look carefully. The balloon has now collapsed. It looks very sorry for itself. But if we allow it to warm up a little bit by shaking it up, throwing it up in the air in a very short space of time, let's see if I can catch it. I'm sorry, it's escaping from me. It's escaping. And as you see, it has been restored to its full shape. Now, why is that? Because at the warmer temperatures, the molecules have more energy, and therefore they move faster and move more rapidly. Now, let's just carry on to my favorite topic, which is fire. This flame here represents one of the greatest traditions of the human race, and that is, of course, our ability to make fire. We know that in East Africa, where the first ancient civilizations were 100,000 years ago, people were able to make a fire and sustain a flame. I'm now going to just show you how 10,000 years ago, for thousands of years, flames burnt like this. This is a piece of cotton wool, and you'll notice it's a dreadfully boring flame. It just burns like this. Why is that? Well, because the cotton wool is surrounded by air. Air only contains 20% oxygen. It was only realized that air is a mixture of gases about 300 years ago, and we've been on this planet for 100,000. And once chemists had discovered the oxygen is the vital component of air that makes things burn better, they started either combining fuels with oxygen or mixing them with oxygen. And here I've got a piece of cotton which has been chemically combined with oxygen. Please watch how differently this burns. And we put it in here. And you notice, and it's blown the flame out. I knew it would blow the flame out. Damn it! That's adding an extra 3 seconds onto my talk. Never mind. We shall quickly. I was ready. I had my matches. Now, what I wanted to show you, I've just shown you the world's first high explosive nitrocellulose or gun cotton. I would love to do an explosion with it, but I can't. We don't have the time, so I'm going to show you a propulsion. This here is a mortar. It's a type of device which is used for propelling fireworks high into the sky. I'm not going to prepare fireworks. I'm going to propel ping pong balls. So sorry, I got 4 ping pong balls in my pocket here. I have a cage, gun cotton cage here, dropping it to the bottom. Sorry. Has it gone to the bottom? I don't know. Too bad. I'm going to force it to the bottom. I'm sorry, I'm struggling a bit against odds and against time. Let me just... There we are. I think it's gone to the bottom. If it hasn't, too bad. We're going to shove a fuse in there, and that will hopefully, when this goes off, we'll see it going up to the... We'll watch the ping pong balls fly out if they manage to reach the bottom. If they didn't, that's too bad. We won't see anything. But nevertheless, there goes our fuse. Hopefully, come on, catch fire. Time's running short. Dear me, this is a very bad piece of fuse. So I'm going to have to put my fingers on lift, and there we go. Now, on to the final things here. Here we have, there we are. I don't know whether did anything happen? Yes, they walked out. Now, here we have, sorry, very quickly, we have here a balloon filled with hydrogen, caused a complete sensation among scientists. The lightest gas in the universe going off there. That's pure hydrogen. This is thunder air, aria tonante, a mixture of hydrogen and oxygen, and then it goes like that much louder. Now, for my very fine work, I have here a mixture of hydrogen and oxygen. I have a fuse which I'm going to make here, and this will be my final experiment. We're going to have a thunder and lightning effect here. We're going to have a thunder and lightning. Sorry, everything is going mad. Let's just get rid of this balloon. It's getting in my way. Now, here we are. I'm going to make up some flash powder, fuse powder. This is going to be, so to summarize, what have I been talking about? Chemistry. What have I been selling to you? Chemistry. In simple, direct language, chemistry for all. So here we go, fingers crossed, and there it is. So thank you very much indeed. I wish you all the very best. Thank you for your kind attention. Thank you very much indeed. Thank you so much. I did 15 seconds.
Following Zit's flow is probably not a good idea, but I'm going to do it anyway. He's done a lot of YouTube videos on the Royal Institute site. It's really fascinating. Okay. Anyone recognize this?
It's a dry ice.
Yes, that is dry ice. And dry ice does not melt like water ice does. It has the property where it goes from being a solid to a gas. Anyone know what that's called? Not melting.
Sublimation.
Excellent, sublimation. And when it goes from a gas to a solid, that's also sublimation. So it sublimes. And if I let this sit here, after a few hours, it'd just be gone. There'd be nothing there. So if I add water to it, because of the heat of the water, it sublimes faster. And what is this that you see? It looks kind of smoky, fog-like.
Carbon dioxide?
Excellent guess, because with carbon dioxide in there. So unfortunately, no, because carbon dioxide is invisible.
Would it be water vapor?
Excellent. That's right. The carbon dioxide, even though it's a gas, when it's sublimed, is very cold. And it's causing the water vapor to condense. And is the carbon dioxide gas heavier or lighter than air? You'll notice that this condensed water is going down, not just because the water is more dense, the condensed water, but the carbon dioxide is more dense also. And so it's flowing down. So here I've got wooden blocks with candles sitting on them at various heights. And I'm going to put some dry ice in a beaker here. Hard to find the right size pieces. Now I'll add some water to that. Oh, one of my candles got blown out. You may have seen an old movie called Mr. Mom, where the mother has to go to work, the father stays home, and is completely, you'll notice as the carbon dioxide builds up, it's putting out the candles. Here I had some dish soap in water, hot water, and the carbon dioxide is forming bubbles with the dish soap. And this last candle is on its way out. And here I have 3 different solutions. These are water with a little bit of sodium hydroxide in it. It's a base, so that they're at a high pH. And I'm going to add some dry ice to each one. I'm not done with that one. So just dump that out. What was I doing? Oh, dry ice. Does carbonated beverage taste different than a non-carbonated beverage? Notice the colors of these. They have indicators in them that change color at different pH. Hopefully, you do taste a difference. Nope. Used to doing this in larger graduated cylinders. So, what you've been looking at are physical changes, changes in physical properties, except here. Because carbon dioxide, although it's solubilizing in the water, it's also reacting with the water. And it's carbon dioxide that gives your sodas fizz. Well, the carbon dioxide reacts with the water and forms carbonic acid. And that carbonic acid changes the pH. And so that's why these are changing color with the different indicators. Now if I can find problem with big fingers. Can I get you to get the wand out of there for me, please? Great, thank you. So you're seeing drastic changes in colors here due to that. They're not lasting long enough. We need more hot water in there. You may have noticed in here, got some 7-Up and some raisins. What's been happening? Yeah, they're going up and down. Why? What makes something float?
Their density is changing because of air bubbles.
Excellent. the air bubbles are attaching to the rough surfaces, they're called nucleation sites, on the raisins. And the system of the raisin and the air bubble, I'm sorry, not really air, carbon dioxide, causes it to have less density, it's more buoyant, and it rises. When it gets to the top, the bubbles come off of the raisins and they sink back down. It's a demonstration called dancing raisins. And you'll notice that the bubbles are floating. And that's because the carbon dioxide is more dense, staying on the bottom, and the bubbles are floating on top of the carbon dioxide. And in my classroom, I used to reach in and grab a bubble and say that it was so cold it got hard, and I'd bounce it. But I was cheating. That was a magic trick. I also have a lava lamp there. It's taken hours for it to work, but there's little balls that are going up and coming back down, and they're quite malleable. And that's because they're a kind of oil, and there's a lamp underneath it that's heating them. And so they rise up. As they get up there, they cool off, get more dense, drop back down until they get heated up again. Okay. What else? Pick a color. Pick a color.
Green. Green.
Blue? Green. Green. Sorry, I couldn't hear you. Now the real question is, can I get this? Small enough. Now, dry ice is very, very cold. And we say it burns the fingers, but that's because it feels like it's burning. The nerve endings don't like it. So you should never handle it without gloves. And preferably thicker gloves than these. Don't have the dexterity I used to. Okay, I have one more physical property I wanted to show you. Because the physical property is called conductivity. And this is a long copper tube. And I'm going to try dropping two different things into the copper tube. And try to notice about how long it takes to go all the way through to hit the bottom. Listen for it hitting the
Can we
carpet.
zoom out real quick?
Pardon?
Can we zoom out the camera so we can see the
Okay.
both ends?
Give a better surface for it to bounce. So that's how long it took. Now, releasing magnets. Much, much slower. Anyone tell me why that is? Okay, property is called electromagnetism. Magnetism creates electricity, electricity creates magnetism. As the magnets drop through the copper, they create an electric field in the copper. And that electric field, in turn, creates a magnetic field pushing against the magnets. So they drop much, much slower than something that is not like that, is not magnetic. There we go. That's called a whoosh bottle because it goes whoosh. I've lost my piece of paper.
Do you think that the cold temperatures may be retarding the reaction?
Maybe, but it really shouldn't have that much of an effect. I got to grab some. Now, Sislo demonstrated flash powder. I'm going to show you flash paper. Then impregnated with something to make it burn very fast. And there goes our spontaneous ignition of the gummy bear. That is all the energy released from one gummy bear. And if you eat a whole pack of gummy bears, are you going to have that fire in your tummy?